Sweet. Should we let's get Jens's slides up. I think that'd be a nice way to show everyone what we're going to be dribbling about. We'll give it another minute, let people trickle in, and then get started. Yeah. So I just pinged everyone in the Discord chat about this talk. So yeah, massive shout out to Justin for making this StreamYard thing possible. Otherwise, I think we'd all be locked out and have no idea how to gain access.
So cool.
Damn, the talk hasn't started. We've already got questions. That's great. Yeah, so I guess we'll find out.
Ooh, that's a really good question, actually.
Yeah. Yeah, cool. I think that's good. Let's get going. So yeah, welcome to today's Open Neuromorphic talk. This is an exciting one, partially because I have a personal vested interest in it, but no, basically a bit of background, right? So it was the 2023 Telluride Neuromorphic and Cognition Workshop in how long ago was that now? 8 months ago, right? So we all met each other. We were all just a bunch of nerds conking out our own open source neuromorphic project. Some of us on hardware, some of us on software, some of us on both. So it was quite a large team and a lot of people that were very interested in it. And we're all kind of going towards the same goals. We're going about it through slightly different ways here and there, be it different libraries, different techniques, different hardware platforms. But you know, in the same way that you've kind of got PyTorch and TensorFlow that also effectively are trying to achieve the same ends, but in different libraries or different languages, we were kind of, well, Jens specifically made this observation that do we want everything to go super disaggregated? Like we want to kind of balance this need between everyone having the same, everyone being able to build off each other's contributions while still retaining some sort of individualization, right? Everyone still has their own unique goals in the neuromorphic space. So we don't want to branch off too much, but we also want to keep things building on top of each other. Those conversations led to us all kind of working together on this neuromorphic intermediate representation that, like, I'm not going to go deep into it, so I'll let Jens discuss, but it lets us hop between different Python libraries, different spiking neural network libraries, and it's not just constrained there, right? So yeah, with that being said, I'll give a brief introduction to the people that are going to be speaking, I suppose. We've got Jens. So Jens is a PhD student at KTH Royal Institute of Technology, very royal. He's the he's the mastermind behind the spiking neural network library Norse and AE Stream. So he's clearly an avid contributor to the open source neuromorphic toolchains that are out there. He's done a lot of cool work. That's basically how we met. Recently, he was awarded a NeuroPack fellowship, so he's going to be coming up the road to Stanford University. So I'm excited to steal him for a little bit and show him my favorite restaurants in Santa Cruz. We've also got Bernhard. He's a PhD student at TU Dresden, and he's working as a research scientist with Christian Meyer on the Spinnaker 2 team. So there will be a focus on how to get spiking neural networks from perhaps trained in one library into a library that's compatible with Spinnaker 2 and actually get these things on hardware. And Felix, who is looking beautiful there with his hair down, He's a senior R&D engineer at SynSense. He'll be going us through how to port these same models onto their edge accelerators, Speck and Xylo, one or the other. So yeah, this is cool stuff. It's all about getting models into different formats and getting them onto hardware. So without further ado, Jens, it's all you, baby.
Wonderful introduction, Jason. I'm really flattered by the introduction, but also think about the energy there. But I mirror that enthusiasm, because I think this is a topic that touches a lot of the community, not just because it's something we concocted in this weird workshop 8 months ago, but we actually managed to spread this to quite a lot of platforms. So I think a lot of people can benefit from this, and I think a lot of ways to take this. And so before we get into the nitty-gritty detail of what the neuromorphic intermediate representation is, I'm going to say NIR from now on, just to avoid these annoyingly complex words. I think I want to talk a bit about the problem, because there was a particular problem that we've been facing in the community for quite some time now, that I think NIR is trying to address. And the specific problem actually pertains to something I think was written really eloquently by Sarah Hooker in Archive paper from 2020, where she talks about the hardware lottery. Right, so she philosophized that it turns out that good research ideas wins because they are compatible with what exists in terms of software and hardware. It's not because the idea is any better than any one other idea, right? Maybe we can have wonderful ideas to build whatever photonic platforms or some other kinds of substrate, but if you don't have the hardware to run these things, you're not gonna go anywhere. I think that's a really important and poignant observation, particular for the neuromorphic community. Nothing said, nothing forgotten. And then I want to take you back in time, and this is from 1958. Right? I mean, people have thought about this for a long time. John von Neumann, in his book *The Computer and the Brain*, talks about how the nervous system is actually based not of one type of communication, but of two types of communication: those that do not involve arithmetic and those that do. And so jumping from the hardware lottery into the realm of biology of the brain, it turns out there are competing paradigms here. It's both working digitally and in analog. And that's really the problem of neuromorphics, right? Because neuromorphic needs to encapsulate, it needs to describe it. So the digital representation for brains is just not sufficient. And there's another really cool paper I can recommend from Catherine Schumann from 2022 that talks about the tremendous opportunity when we can co-design across the compute stack. So we can melt the software and the hardware when we build these neuromorphic systems. And the need is exactly because for the reason that John von Neumann mentioned, that we need to combine this digital and continuous time analog representation. Otherwise, we just will not win the hardware lottery. And I think the problem in neuromorphic communities has been, how do we then do this co-design? How do you do it? Because building neuromorphic hardware is extremely complicated. Thinking up neuromorphic algorithms is extremely complicated. What do we do? And to make matters worse, I mean, we're fighting an uphill struggle, because it's clear that deep learning won this hardware lottery hard, right? They're really piggybacking on the wonderful, and I don't want to diminish the efforts here, right? It's tremendously important work, like for civilization. Just think about the recent developments in large language models, right? It's obviously tremendously useful, but they clearly won the hardware lottery. And the reason why they won this hardware lottery is because this idea of an artificial neuron, the rectified linear units and the convolutional nets running on GPUs, is just taking over the world. And one particular reason why I think it's going so well is because they've really solved this matter of interoperability. You may have oddities in your model that you need to study from the scientific perspective in PyTorch, but you can still run it in all the different platforms. In CPUs or GPUs or whatever else. You may have oddities in your model in TensorFlow that you're trying to study, or in JAX that you're trying to study, but you can still work with it in different platforms, exactly because there's this integration, this interoperability between different frameworks and systems. And we don't have that in neuromorphic, right? I hope I'm not offending anyone when we say neuromorphic platforms are completely disparate. So flash back to 2008, where Jason took this wonderful mugshot of us brainstorming about this problem. Right, this has been a problem for many, many years. What do we do about it? And this bunch of, I wouldn't say misfits, but this bunch of naive students got together and said, okay, what about taking inspiration from the deep learning? What about doing something like ONNX just for neuromorphics? And that's basically what came out of this. And this is what NIR is. It's a massive effort by a ton of people. That's some of them are listed here, that really came together. It's quite unique. I haven't seen something that big, I think, around this kind of open source effort. It managed to connect 11 different neuromorphic platforms, both simulators and hardware, that then works and interoperates just like the ONNX specification. And the idea is exactly to have something like ONNX, so that NIR is kind of in between, and then we put the simulators on top and the hardware on the bottom. That doesn't mean that everything flows from the simulator to the hardware. In principle, the arrows are bidirectional, so you can go from snnTorch to Lava, and from Lava to Intel, Luigi, and so on and so forth. So there are multiple movements here, back and forth into NIR and from NIR. And the reason why I'm really particularly fond of this model is because this is one of the first kind of pure models that can reproduce neuromorphic computing in its pure sense. And let me tell you what I mean by the pure sense. Because NIR does not describe discrete digital instructions. They describe idealized continuous models. So formally, they are hybrid systems. So they both consist of this discrete digital representation of spikes in the brain, but also have this evolving, time-evolved differential dynamics. One example could be the leak integrator. You can see, you can describe this as how the voltage evolves over time, depending on some leak and some input and resistance. So this would be one example of a system that kind of works over time and integrates some current, and then leaks away some of the let's say data in this case. And what we did then in the paper is to show, okay, it turns out that if we agree on this idealized continuous time model, then we can take that description and we can run it one place. And then we can take that same description and run it in another place, and then a third place, and then a fourth place. And we can try to run all these things at once, simultaneously, and see how do they compare. What is the behavior across all these disparate different systems? And what we find is that we're not all in perfect agreement. We don't have, because of the hardware details and the different platforms, we don't have a perfectly correct or similar representation, but we have a very agreeable understanding. So you can see at the top here, you have the input coming in, the input spikes, and this is then the membrane voltage evolving, so the potential over time. And down here, you then see the spikes coming out for the different platforms. So you can see there's a bit of difference, but mostly it looks very similar. And I think that's a beautiful analogy to neural system, which are just by definition in nature noisy, chattering. It's not an exact representation as you would have in digitally clocked systems. And that's, you might argue that's a problem, right? Why even bother with representation if it's not correct? But I think it depends on your level of or understanding or definition of correctness. So back to the paper, another example we did was to take a convolutional neural network and see, okay, what happens then if we take a convolutional network defined in this neuromorphic intermediate representation, then we send it to the different platforms, and then we measure what activity appears in the networks and how does that activity compare. So specifically what we do is we take the cosine similarity. So we're basically comparing the angles of two very high dimensional spiking vectors, if you will. So a 1 means perfect similarity, and less than 1 means more and more disparity, more and more difference. But remember, it's a very high dimensional number, so The one is a very, very close proximity. And what you see is also a lot of agreeability. There are some simulators that have different dynamics. We can see that, and specifically some hardware that have different dynamics, because hardware is very difficult to build, as we said. And there will be particularities in terms of time constants or restrictions in compute capacity, and so on and so forth. So I think it's fair to say that we can, in NIR, describe this idea model. But the ability to see this mismatch is not because the ideal model is wrong. That's because when you work with digital representations of these models, you're forced to discretize the integration somehow. You need to figure out how you break down this continuous time into a sequence of steps that digital clocked systems can handle. And that's actually, I think, an incredible strength of NIR, because the NIR definition doesn't change. It's still the same graph, it's still the same NIR model, but it allows us actually to reason about the, let's say, source and target platforms. Let's say if I train a model in snnTorch and want to put that on Spinnaker, I know where I want to put it, so I can be aware of the Spinnaker 2 platforms, specifications or idiosyncrasies or discretization choices. I can train things and optimize things specifically for specific platforms while having the same idealized model. So more specifically, NIR looks like this. We have our representation here, and as I said, this is just a graph. It's just some blocks composed together, and then some signal flows from one end to the other. There can be recurrences or duplicate connections. It's basically an arbitrary directed graph. But then we have to figure out what we're going to do with that graph. How are we going to evolve it or evaluate it? One thing could be to evolve it or evaluate it in discrete time, just like we saw for digital simulations. And then we have to break it down into clocked sequential steps. And then you can put that either in hardware or in some kind of simulator. You could also, in principle, take the idealized continuous time, keep it continuous, and then you can use continuous time simulators. So simulators like Brian and Nengo, I think, are much better than most of the deep learning simulators to then really faithfully reproduce the continuous time integration. But in principle, you could also take this to analog mixed hardware signal. We haven't done that in the paper, but there'll be an obvious, an interesting next step, I think. And so when we have this graph, we literally just take the nodes and connect them together. So this might look a little bit weird to you, but I think it's a very informative representation for you to see. This is just text. It's just a way to represent these things in a textual and symbolic form. Because NIR does not implement the leaky integrator or the linearity. It literally just says, this is a leaky integrator, and here are the parameters. When you take this graph, you know how to implement, how to solve, how to evaluate these different computational primitives. That's not the job of NIR. That's the job of the platforms. And we're going to show you later a few demos, but I'm particularly fond of how easy it is to work with this thing, because for any end user, there's no need to know how NIR works in principle. You can just work with whatever framework you're used to, if that's snnTorch or Lava or Norse or whatever else. And when you're done with your model, so let's say you have some kind of deep learning model that can learn to detect faces or something, you just say, okay, please take this model and put it into this intermediate representation format. And when you have that format, you can then go to any platform that supports it and said, okay, I have my model, let me load it in and then run it. In this case, I'm importing Synapse, which is a product from SynSense that's used for their Speck chips, for instance, which we're going to see in a few minutes. But the cool thing here is that you don't need to know anything about Synapse or Speck. Of course, there's a chance the Speck doesn't support your primitive. In this case, this is going to blow up and it's not going to work. But as long as you follow the principles and the building blocks that exist in that platform, this is going to work. You can just take the representation you have in Norse or in snnTorch or in Lava and dump it straight to the neuromorphic trip. This is to me true interoperability. I think that's an absolutely wonderful feature. Of course, this is just the beginning. We still have a lot of primitives to implement and complexities to work out. But we showed in the paper that it works for 3 types of networks: this leaky integrating fire plot I showed you in the beginning, a spiking convolutional network, and a recurrent reservoir model. So this is not just toy examples in the sense that these have actually been used in publications. So they're useful, and I think already these primitives are quite general. We'd love your input and see what you think. But I think before we move on to questions, I think it's a good idea to demonstrate this to you, to show this actually works. So I think without further ado, we should probably just continue with a few examples on how this works. So we prepared 3 things for you. In a Git repository I'm gonna send to you in a second, so you can play around with this by yourself. I should say that, of course, this is in the context of open neuromorphic, so we've made sure everything is open source and you can go home and reproduce the result yourself. But we prepared 3 examples for you. One thing is in Norse, where we're just going to train some random convnet in nmnist. That's going to give me a NIR graph. And then we can take that NIR graph and we can send that to the Speck chip by SynSense, which Felix is going to demonstrate. But we can also send that to the Spinnaker 2 chip, which Bernhard is going to demonstrate. And so this will give you a flavor of how these things actually work. And hopefully you'll realize that it's relatively seamless and works relatively well. So finally, I should mention that Jason Eshraghian, who did the wonderfully positive and optimistic introduction, is going to take over and talk a bit about how this generalizes and work in the further ecosystem and for future neuromorphic hardware platforms. So without further ado, I have the honor of starting talking a bit about how we go from Norse to NIR. And again, let me remind you, it doesn't have to be Norse. It can be snnTorch, doesn't matter, as long as we have some way to generate a NIR graph. So what I prepared for you is a simple notebook here. So I'm just going to demo how we can create some kind of convolutional neural network. And I'm just going to walk through the code. And I know this might be a bit geeky and involved, but for those of you who've worked with deep learning or spiking neural network libraries, I think you'll find this relatively vanilla. I'm not doing anything fancy or magic relative to all the work you need to train deep learning models. But please interact with us, ask questions, stop me if there's something that's unclear, and we can talk about it. This is supposed to be understood by everyone here. But let me try to pedagogically walk you through what's happening, and just I'm basically showing you how the sausage gets made behind the scene, because there's really no magic here, and it's relatively simple and understandable for most of you. So I'm just going to import snnTorch, and then I'm just going to create a very, very simple model. And this is a very relatively dumb and uninformed model. But what it's supposed to illustrate to you is that we have some leaky integrating fire cell, some convolutions, and some pooling. And eventually, they're going to give us 10 different predictions, because, again, we're predicting digits. We are figuring out, are we looking at a 1? Or are we looking at a 2? Or are we looking at a 7? The data format is a little funky. It's from the neuromorphic MNIST dataset, which means we actually have time-stepped data. So we have a video of images coming in, where the images then consist of the event data. So event camera, positive or negative polarity input. So that means we have some time steps with 2 polarities, positive and negative, in a 34 by 34 grid. So when I create this model, which again is just a sequence of different neurons and convolutional layers, when I create this, you can see then that I can try to give an empty tensor into the model, and you can see when I ask for the output, it gives me, okay, now I put in 1 batch of input, and I'm going to get 10 outputs. So those 10 outputs represent the 10 digits. And ideally, later, one of these outputs is going to be higher than the other 9. And that means that this model predicts, okay, this is the digit. So let's say that the 9th output in higher than the other 9, that means, okay, this is I predict that the input I got is was the 9th digit. And so already now I can actually take this into a NIR graph. And the reason why this is very cool is because even though this is a completely untrained model, I haven't done anything. Torch just randomly initialized those parameters. You can see I already have a model. And so in Norse, there exists this function called toNIR, and it's similar in the other libraries like Lava and snnTorch and so on, where I can just take my model and then dump it into a NIR graph. You might ask, why do I have to give it this torch empty? Well, for the same reason that I'm giving torch empty into my model to begin with. And this is a peculiarity of PyTorch, because we need to do what's known as tracing the computational graph. We kind of have to go through the graph step by step to know what order of the layers are being executed. So we know that first is the lift cell. Okay, that's going to be the first node. Okay, then comes the convolution. Okay, that's going to be the second node. That means I have to take the lift output and send to the convolution in the NIR graph. It's just a technicality, but this is why we need to inform or feed in some data when we generate the NIR graph. But what I want to show you now is that I can basically just take the nodes. You can see I got the graph got some nodes. So those are those computational primitives I talked about before. The names are kind of uninformed because I haven't given them names here. Just call them 0 and 1 and 2 and 3 and whatever. It doesn't really matter. But the cool thing is that it also have some edges. Oh, I can just do like this thing, which is just a list of how things connect together. And it's not ordered, so it's going to look a bit jumpy, but this is literally the text that I showed you before in the slides, right? It's just saying I have these nodes, and the input is connected to the first node, and the first node is connected to the second node, and so on and so forth. So it's a super simple graph representation. And just to show you how this works, I'm just going to demo how the training can optimize the parameters and then change the underlying values in the model. And this is going to be probably familiar to a lot of people here. So I'm just gonna go over this. Again, this is going to be on YouTube, and you're welcome to ask questions. So if there's anything that's unclear for you, please engage. But I'm going to import a TQDM, which is a progress bar library, so you can see what's happening, and then Tonic. And since this is an open neuromorphic talk, I should give some advertisement to Tonic, which is the awesome work of Gregor, among many, many others, who's been collecting neuromorphic data sets into one data set, which makes it incredibly important incredibly simple just to import data sets like this neuromorphic MNIST. So I can just say, give me the neuromorphic MNISTs, convert it into frames so I can send them into my model frame by frame, and then wrapped in a PyTorch data loader. And the reason why this is really cool is because I now have a complete data set, and you can see this is then the time dimension. So I have 308 frames for one specific data sample with 2 channels in a 34 by 34. And so now I can start training this. And without explaining the code in too much detail, I just want to say that I want to show you this number over here. I just want to say that I'm taking some of the parameters in the model, optimizing them, putting the model on an NVIDIA card because that's a bit faster, just running through all the data samples in the loader, putting it through the model, and then finding out, okay, what's then the loss here? I'm not even doing any optimization, as you can see, but that doesn't really matter. I can just slowly kind of calculate the correction and get that out. So you can, let me just stop that here because we don't want to wait for this. And then you might ask, okay, now we have a model which has probably been changed a little bit, even though I realized I forgot a line to actually run the optimizer. So I apologize for that. I'll add that in the repo in a second. But the point is now the model has changed. So we've altered some of the parameters and we've changed it a little bit. And that's similar to, let's say, adapting it to a certain platform. So another example of this would be that we know that we're now going to run it not in a Spinnaker chip, but in a Speck chip. That means we should probably adapt the model a little bit so that it works better for the Speck chip compared to the Spinnaker chip. And we can do that again because we know how the integration scheme on Speck or on Spinnaker works. But the outcome remained the same. We still have the model, and the only change was going to be in the parameters. So we can then take this NIR torch to NIR function again and just dump out the model. And what you see here is exactly, again, what you have before, a NIR graph, bit more verbose. We have the nodes, those are the inputs and the leaky integrating fire nodes, and we have the edges in the end, which then describe how the nodes are connected. So I hope this explained to you, first of all, how this is very, very vanilla. This is very close to what you've done before. You actually basically just need to output things to NIR, and then you're done. That's pretty much all there is to NIR. The question then becomes, now that we have this NIR graph, what can I do with it? What happens to it? Why would I even bother putting this to NIR graph in Norse? And the answer hopefully comes when Felix in a minute is going to take us through the Synapse and the Speck stack. Because now we can take such a spiking convolutional neural network that we just built, dump it into this NIR representation, and ship it off to Felix. So without further ado, I'm going to hand it over to Felix, who's going to show you how this works for the Speck chip, which is, by the way, a super cool piece of hardware that I recommend that you all try out. I'm not saying that because I'm not paid by SynSense, don't worry.
Yeah, thanks for the compliments, Jens. So I'm Felix from SynSense. I will give a very brief overview of SynSense and the hardware we will be using right now in this demo, just to make sure that everybody is on the same page. And then I will use a NIR model that Jens has trained before and deploy it on Speck to see if it really still works. So SynSense makes neuromorphic hardware for low power applications at the edge. Our devices get some sensory input and then in real time process that to provide a highly informative output, but at a low bandwidth. So this could be, for example, a wake up signal whenever there is some specific condition being detected in the input. All of this happens at a low latency in the order of a few milliseconds and at low power, usually below 10 milliwatts, sometimes even lower. There are two main hardware families. One is the Shiloh chips. Those are mainly for natural signal processing applications. And then there's the DynapCNN Speck family for low power vision applications. And Speck is the one that we'll be looking at now. Speck is a system on chip consisting on a dynamic vision sensor and a fully asynchronous digital spiking CNN processor. All of that on one tiny chip. Try to hold it into a camera. You see it here. That's the dev kit. And the chip itself is this very tiny package up here. The way it works is the events that the vision sensor generates are streamed to the spiking processor and they're processed in real time. So you can deploy a spiking CNN of up to 9 convolutional layer plus pooling and optionally a dense layer. As Jens has also mentioned before, there's great hardware needs great software. Otherwise, it won't get far. And therefore, SynSense is also very actively contributing to several open source neuromorphic projects. First and foremost, of course, NIR. That's why we're here today. But there's also Rockpool, Tonic, and Synapse, for example. And Synapse is the one that we will run the demo with. It's PyTorch. It's based on PyTorch and can be used to train and deploy spiking neural networks, especially for the Speck family. Okay, let's dive directly into the demo. So I've prepared this notebook here for you. We'll start with some imports. It's partly for plotting. The most important lines here is import NIR and import Synapse. What we first do is we will load the NIR model that Jens has trained before in NORS. And for that, we just need to run NIR.read and then a path to this model. Now, to get it into Synapse, which is the library we will use for this demonstration, we call the from NIR function within Synapse. And to make things a bit faster, I first deploy the model on a GPU. So now the model is imported into Synapse. It's not yet on Speck. It's purely on my PC. And I deploy it onto a GPU just to see, has anything changed? Does it still work? So I will load the data up here. I will, of course, use Tonic. I, again, have to transform the events, the raw events from the data set into frames, exactly the same way as it has been done for NORS. And then I will just run through a small subset because I don't want to go through the whole test set. That would take a bit too long. And then sample by sample, we'll just run it through the model that has been imported into Synapse. And then in the end, calculate an overall accuracy. Here we go. We see the accuracy is 96%. So it seems that the model is working fine. And we can go on to the most interesting part and deploy it on Speck. Until now, when we imported the model into Synapse, it's maintained the graph structure that it has received from NIR. But for Speck, we want to convert it to a purely sequential model. For that, we'll just quickly iterate over the Synapse model and basically flatten it out. Another small modification that we need to do is in NIR, parameters such as thresholds, spiking thresholds, are saved per neuron. However, Speck wants these parameters on a per layer level. So every neuron in one layer shares the same threshold. And so here in this loop, we just go over all the spiking layers and make sure that the spiking threshold is the same for all. And then finally, we deploy the model here. So we convert it to a class that's called DynapSNN-Network. That's the class in Synapse that is used to interact with Speck. And then, just like you would do in PyTorch, we use the .to method to deploy it. So now this will take a few seconds. Now it says network is valid, means it has been deployed properly. Okay, before we can send in data to Speck, we need to again prepare a little bit our data set, because this time we need to send the data event by event as it is in the data. So we don't do this conversion to frames because Speck is purely event driven. In this cell, I defined some helper functions. This is just to make some nice plots. You will see them later on, but there's no real magic going on here. And then finally, this is where the interesting part happens. I put together a small function here where you can provide a class as an argument, and then it will just randomly choose one sample from the test set that corresponds to that class, and then send that sample to Torch. Sorry, not to Torch, to Speck. Read out the output from Speck, and we'll see if Speck predicted correctly. So now let's just start with the number 8. So what we see here in this plot is just a heat map of the input data. It's a bit blurry because all the spikes are now integrated over the full length of the sample. And here we see the prediction of Speck along with a histogram showing for each output neuron of Speck how many times it spikes. The idea is that whichever neuron spiked most is the one that makes the prediction. We see here it's neuron 8 that spiked most, and Speck predicted the class correctly. You can try with another number, let's say 6. And again, the prediction is correct. So it seems that it's working pretty well. If we want, I will leave that to you. It will take a bit too long to do that now. But if you want, you can iterate over that data set here with this cell, and then just deploy sample by sample to Speck and see how well it does at the end. Okay, summarizing, we have implemented a model from NIR that has previously been trained in a completely different framework, NORS. We've imported that model to Synapse. We've made sure that in Synapse, this model still works. And then we've deployed that model onto Speck. And we see on Speck, it is also still working. And I think this is pretty fantastic. It's never been so easy to develop different spiking neural networks in a larger range of different tools, and then from there go easily to your hardware of choice and deploy it there. And to show you that this does not only work for Speck, Bernhard is now going to show you that it can also be deployed on Spinnaker. Bernhard, you're muted.
Yeah, I meant note. I see. Okay, yeah, thank you, Felix, for the very nice demo. Now let's go to Spinnaker 2. Let me also give a short introduction to the Spinnaker 2 chip for those who are not familiar with it. So the Spinnaker 2 chip. So this is Spinnaker is the first generation Spinnaker was developed in the University of Manchester, and then in the Human Brain Project for a period of 10 years. The second generation system was developed at TU Dresden and in Manchester. And I mean, this figure is a bit, it's very full, overloaded. But let's look at the center. This is the Spinnaker 2 chip. So this chip, as the inventor, Professor Steve Ferber, he's one of the ARM fellows who invented the ARM instruction set. So it has like 152 low power ARM cores. And the idea is to have a highly distributed software-based simulation of spiking neurons, in this case, in a scalable system. Yeah, so we have a chip architecture with many processing elements, with software running on the ARM cores, but also with accelerators for certain functions. Like we also support deep neural networks, so we have a MAC array, and we have specific accelerators for example, for the exponential and the logarithm function, right? And something special which makes the system scalable, there are these so-called Spinnaker routers for sending spike events across large systems, from systems with whatever, 1 chip to 48 chips to thousands of chips. Yeah, you see in the top left that we are currently building up a cloud system with 5 million cores. Yeah? So this will be available in the course of this year. What I'm going to show now is an example on the single chip board, which you see here on the right. And just to very quickly explain the SNN simulation here. So we have these ARM cores, and this means that each core runs about 250 neurons simulated in software with typically it's a 1 millisecond time resolution for the neuron dynamics. Each core runs locally synchronous. Of course, it's clock-based, but they are not synchronized globally. Yeah, and they just communicate through their spikes. I can also show the hardware that's here. So this is the board. The chip is in the center. And now let's look at the software that we're using. We are not using like a deep learning library for developing our models for Spinnaker 2 right now. Or I mean, this is not the API, but the API is rather looks like Pine, so PyNN, which is whatever standard for defining more biologically realistic spiking neural networks. So it's based on populations and on projections, right? And this is how a spiking convolutional network would look like if I had to define this from scratch. Yeah, so I would define an input population with input spikes and then several populations with 2D convolutional layer neurons. Yeah, and I have to define special projections. These are like the connections between populations. And then I need to add all these populations and projections to a network, and then I can run this network on the hardware. So the good thing now about NIR is that I don't need to define this. So I can just import the NIR graph that was trained in another framework, for example, in NORS or Synapse or snnTorch, and deploy it, convert it to this Spinnaker 2 format, and then run it on the Spinnaker 2 hardware. Now let's move on to the demo. So thanks to Felix, I had a template for this Jupyter notebook. So I'm going to show exactly the same network, but now run on Spinnaker 2. Thanks also go to my colleague Matthias Jobst, who helped with the implementation on the Spinnaker chip of this model. So we again start with imports, and we also again import NIR here, and we import some modules from Spinnaker 2 library, which is this PySpinnaker 2. This takes a few seconds, and then the next step is again I load the same model that was used before, and also read it, and then I quickly run it, and I need a custom command here, NIR graph infer types. This provides all the necessary shape information of all the nodes, so that I know how large each convolutional layer is, for example. And then it provides like a model summary of which nodes are in here. And then it's the next step. I need to convert this NIR graph into the PySpinnaker 2 network format. I can customize this translation. So for example, I can define which parameters I want to record, or which variables I want to record from the output layer, which is in this case the voltage and the spikes. I define the time step that I would use for the conversion of the neuron model. I define how to scale the weights if I adjust them to the dynamic range of our system. Currently, we use like 8-bit unsigned integers for the weights, and floating point values for the neuron dynamics, neuron parameters. And I can define things like the reset method for the integrate and fire model. Yeah? And then this is the most important thing. I can just call this function from NIR and convert the NIR graph into a PySpinnaker 2 network, and a list of input populations and a list of output populations. You'll see this output here, and then there will be like 6 populations created with certain names. Don't want to go into detail, but now I've loaded this into this PySpinnaker 2 format, and now come the next step. So I again load this neuromorphic MNIST data set. Again, I choose a subset. And last but not least, I deploy the model on the Spinnaker 2. First of all, I do some customization. Like for some of the populations, I need to customize how many neurons there are per core, right? So if I have a large population of like 4,000 neurons, this will get split onto many of these 152 cores on the chip, and I can customize that. And I currently need to do this because this is not fully automated. Yeah, so otherwise I would require too much memory in each core in this case. Yeah, so currently this needs to be done manually. Yeah. Then I have a function for converting the input data into spikes. Yeah, so I take these frames that were used in PyTorch and convert this into a list of spike times for each of the input neurons. Then I have a function to run a single network on the Spinnaker 2 chip, which requires a hardware instance, which is like the connector, the handle for the hardware, and the input and the output populations, and the input data, which is X. What I actually do here is I first convert the input data into spikes. I set them as parameters of the input population. I say that I run this model for a certain number of time steps, which I determine here. Then I reset the net. I need this for a repeated simulation. And then I run this network on the hardware for a given number of time steps with some time step, like this is the system tick on how often the neurons are updated for the next time step. Yeah. And then after the simulation, I get back the voltages and the spikes and return them. So this is just the definition. And then I have some more helper functions. The first one is this histogram plotting. That's the same as Felix showed. And the second one is this function to run a single sample, right? So we again choose a single sample from a given digit. Then I define a handle to the hardware. In this case, this is connected through Ethernet, so I choose the IP address. Then I run the single model, get the results, and plot it. Let's try it with a digit of 9. This will show a lot of output here. It shows that, okay, we have 152 cores available, but we only need 46 of them. And it will start to run everything. We configure the hardware. We're loading all the instruction memory for all the 46 cores. And then we send the input data, run the simulation, and get results back. And then this is again the input image, and then I can show the prediction in this case, and we see that the 9 is correctly predicted. Again, at the output layer, I just count the number of events or spikes. Of course, I can rerun this with a different digit. And it shows again the same output. And the prediction is again correct. Yeah. I'm also not showing this now for a larger data set because it takes too long, because our current software is has to load like all the weights and the instruction memory for all the cores for each run. This is this multi-run support is not available in the main branch of our software yet. So that's why I would skip to show this. But yeah, I mean, this is what I showed, that taking a NIR graph, I can load it. I can customize. Let me check. I can load it. I can customize how I convert this to Spinnaker 2, and then I can run it. Yeah, with this, I'm ready. And I would like to thank you and hand over to Jason.
Cool. Yeah, thanks a lot, Bernhard. So what have we seen so far? We've basically seen a pure software pipeline, a model on its own being trained and ported onto two vastly different spiking neural network hardware. So Spinnaker 2 is not necessarily spiking neural network specific, right? It's a bit more general, but effectively the same model or slightly variant models have been able to be moved over to hardware with different purposes that are accelerating sparse workloads. So I want to kind of capture things in the hardware landscape where NIR has a lot of potential in, and where that might take us in the future. And then I'll just kind of say what we've already said, to summarize what NIR is, I guess, aiming for, right? So the variety of hardware platforms out there, we've, I think we can see my cursor here. Bernhard just showed us how we can move models onto Spinnaker 2. And Felix showed us how to get things onto the SynSense hardware. So they've got Xylo and Speck, one for computer vision models, one for signal processing, lower dimensional data processing. The way that this here has been separated out is it's somewhat debatable, right? So on the left-hand side, I've called it analog hardware. In the middle, we've got digital hardware. On the top row, you have continuous time, and on the bottom row, discrete time. What does this mean, right? So continuous time I'm using in the most general sense. So this digital hardware is basically using values that have been quantized, but over time, things have not necessarily been discretized. That is to say, the digital hardware that you see here, which includes Loihi, Spinnaker, True North, and Xylo, they operate asynchronously, so they're clock-free circuits. Things are going to basically be, data is going to be processed at the onset of a spike. So it's basically data-triggered computation. Whereas the discrete time alternatives, not so much focused on asynchronous circuits, they're synchronous. They rely on a clock to keep everything working. But from the NIR perspective, it's effectively agnostic to these things, right? It doesn't care whether or not your hardware is synchronous, asynchronous. The point is that on the back end, if you want to be able to import a model from NIR, as long as you have your, I guess, your dynamical system equation that could represent your leaky integrate and fire neuron mapped in a way that allows the NIR representation to be converted to, I suppose, your representation if you're the developer of, say, LavaDL or whatever other library out there. As long as that mapping exists, then that's it. Like, then you're able to import from NIR and run things on your own hardware. On the analog side of things, so we've got this shaded out because this does feel like a little bit more of a futuristic exploratory exercise. So what does this mean? Like, of course, Braindrop and Dynapse, they're using continuous time asynchronous computation along with analog computation. But then on the bottom row here, I've also listed out some emerging technologies, something a bit very, very exploratory here, right? So memristive computation, molecular, optical computation, nanowires, and even computing with biological matter. That's referring to the variety of hardware platforms that are not out there, right? And I think that those things are a very natural fit for NIR to use. But of course, there's a lot of problems with that. And it is somewhat related back to this hardware lottery idea that Jens was talking about. A coarse grain example that I think a lot of people in the memristive world have played with already. This was work done by my former grad student, Peng, before she graduated and went on to bigger and better things. She basically created this leaky integrate and fire neuron in hardware using memristors. This is, I guess, a dynamical, you're relying on the dynamics of these memristors, of these weird devices. You scale them up, you've got this sort of sub-threshold looking computation, triggering spikes that very much emulate biology. And why would you do that? Well, it's a natural, efficient representation of many of the primitives in biology, right? You need far more transistors if you need to implement accumulation, if you need to implement some decay. Here, you've just got this minimal set of 2 memristors. You know, this capacitor here can be naturally integrated using parasitics, a bunch of low-level hardware details that I'm not going to bore you with here. The point is that there are ways to use circuit dynamics, the natural physics of things, in order to model biological processes, right? So that's neat. The problem is that it's a very hard thing to control. As a result of it being a very hard thing to control, you don't really have any higher level abstractions out there. You don't have microcode or instruction sets for these types of systems. There is no standard for there is not standard because I wrote these slides during Bernhard's talk, but there's no real standard for continuous dynamical hardware systems. Everything that's out there right now, all the papers you see, they are built completely independently of one another. And I guess that makes sense, right? Because they're not commercial systems. If people are just exploring, they're trying to do things. But NIR is basically a potential way forward, right? If the developers of this hardware are able to map the NIR dynamical system into whatever their hardware, whatever language their hardware speaks, and when I say language very broadly, then you're able to basically port a bunch of these models onto these more exploratory systems. And it doesn't really end there, right? Organoid intelligence has also been this concept that's kind of taken off in the past couple of years. Cortical labs were able to train some neural culture, some 2-dimensional neural culture to play the arcade game Pong. And then Thomas Hartung and Lena Smirnova went on to coin the term organoid intelligence, where you are able to achieve computation using biological matter. The point is, if you're able to identify the dynamical system of equations that exotic hardware represents, then it, in theory, should be possible to be able to use NIR as a way to map from deterministic models using PyTorch, using Norse, using all your fancy libraries out there, and running them potentially far more efficiently on this type of substrate. So just a quick summary, say what's already been said. The point of this is, how can we port dynamical time-varying neural networks across different systems, right? We've got solutions for vanilla deep learning. Nothing but pain has existed for spiking neural networks. And keep in mind, spiking neural networks, that they're not just defined by spikes, right? But leaky, integrate, and fire nodes are basically this continuous time dynamical system until now. So NIR has kind of addressed this. And to go with that, it's this common standard to enable continuous time dynamical neural networks to interface with each other. We have ONNX to do this for discrete graphs, for discrete nodes. But NIR combines this with nodes that are going to evolve over time, which is, again, that's what a spiking neural network really is, right? It's a stateful mode of computation. So we're able to avoid discretizing states in time by having this NIR representation. And it allows the broader community to tap into, well, we're not quite commercial yet, but into the exotic hardware that's out there. This includes Intel's Loihi chip. This includes Spinnaker 2 that Bernhard showed you, and SynSense's hardware that Felix showed you. And yeah, if you missed it, just in case you missed it, the notebooks that they were showing was not running code on just purely in a notebook environment, in a Jupyter environment. It was stuff being run on the hardware that they had on their desks, right? And so this is a real thing, which is pretty neat. So we wrote thousands of lines of code, so you only have to write one, right? You take your model, export it to NIR, and if I want to import something in a hardware-facing library, then I'll go model from NIR, right? So I think that's really neat. And this is obviously not the way that the models are being moved, right? If I train a model in Norse, snnTorch, et cetera, it is going into this NIR representation. But just to really highlight the point of all of this, you take a model that is representing spiking neural nets using stateful parameters, et cetera, and it just gives me a way to be able to take this stuff and move it onto, well, neuromorphic hardware. This includes Loihi, Intel's Loihi, Spinnaker 2. These are large-scale server-based service-scale systems. But at the same time, there's also ways to achieve this at the edge. So that's where SynSense comes in. So with that being said, I think I think we can call it now. We can summarize everything. We can get everyone on the stage and perhaps go through a list of these questions that are, that we were blasted with. We'll get, so we'll start with Christian's question, right? I thought that was really neat. So
can I quickly say one thing before you continue, Jason? Because I think there's a wonderful overview. I just want to say that it's important to know that all this is online, and there is, maybe can we put the link to the repo online, because then people can check it out while we answer questions. It's on GitHub on my repo.
Yeah. So
I'll communicate with the backstage thing, but maybe Jason, take it away. Start discussing questions, please.
Yeah. All of this stuff is reproducible online, so go play with it, break it. No, so Christian is intrigued by the idea of implementing neural control systems, some more, I guess, exotic computations with NIR. So he's asking, could I extend the high order primitive set with the following canonical circuits? So for example, homeostatic activity regulation, winner take all, and Hebbian learning or alike. These elements are, beneficial to implement sensory motor control loops.
Yeah, should I take that, or at least? I mean, I'm curious to hear the other opinions. Like maybe especially Spinnaker, I think would be interesting to this, right? Because it's such a wonderful platform for like very complicated biological problems, which seems to be the one that you're addressing here, Christian. I think briefly, the primitives we have in NIR right now are limited mostly to feed-forward circuits, meaning that you simply just send a signal through it. And so if you want plasticity in any shape like homeostasis or learning, there's still something to be implemented, right? But I will say that all this is just a dynamical system, just like Jason pointed out, right? This is something that nature works with, this differential equation. So if you can describe that, then it's relatively trivial to implement that primitive, just saying, okay, now I'm describing a plasticity mechanism, and here's a differential equation for it. The challenge then, right, and this is then the problem of this approach, the intermediate representation approach, which is also faced by the deep learning community. The problem is that even if you have that idealized description, if none of the hardware platforms understands that idealized description, it's kind of worthless, right? So, there's a bit of lobbying that has to be done if you want to expand primitives, depending on the different platforms. But in principle, adding in primitive is easy. Getting it to run is hard. I don't know if you guys agree.
No, I think we unanimously agree there. I mean, if your learning rule can be recast into a dynamical state equation, which often it can, a lot of Hebbian learning rules are very much like that, then I don't want to say that it would be trivial to extend it, because at the moment, I think the statefulness is constrained to not the learnable parameters in NIR, but it would be very possible to extend it there. And, if there is a good reason, it is very challenging to quantify like some homogeneous sequence or composable set of primitives that contribute to a learning rule. I think it is very challenging to define that. But if it can be defined as a continuous time dynamical system, then it is logical that it can be extendable to capture those. That's a lot for us to think about. Danish asks, so what kind of hardware is suitable for brain-like computing? I think there have been a lot of talks that have gone over this, right? I guess that the two themes that keep coming up, one is asynchronous hardware, that is to say, only processing things when there are new things to process. That's why we like spikes, because if you don't have spikes, then you don't process things. And that effectively removes all the dynamic power dissipation that comes from having to distribute a clock over your chip, having to keep switching wires, high, low, high, low, high, low. So that makes a lot of sense. There's also a lot of fine-grained clock gating, where an alternative to asynchronous hardware is if you don't have spikes, if you don't have that type of computation going on, then you can still have a clock, but you can just turn it off in the time through which there is nothing new to process. I think BrainChip are taking that approach. That's the low-risk design methodologies that are compatible with modern-day EDA tools. The alternative, if you talk to the device community and the material science community, they'll tell you, well, we want to look more at exotic substrates such as organoids. I mean, what better way to simulate a brain than by using a brain, right? And memristors kind of follow the same train of thought. Ion-based computation in memristors could be used to model ion-based computation in the brain. So a lot of various opinions there. Then there is another question. So is the instruction set literal as in microcode, or is that a metaphor? Like,
Oh yeah, that's a very, very good question. Okay, yeah, that's an excellent question, and yeah, it puts spot on, right? Because the problem, I mean, I feel like the neuromorphic field is a bit like where the digital computing paradigm was like 60 or 70 years ago. It's like we have all these ideas of different models, but we don't really know, like, is the LIF model like a general universal instruction that everyone should cater to or implement? So I mean, I would say it's somewhere in between, right? It's a primitive in the sense that it's a fundamental instruction. Meaning, if you have a leaky integrator, it's a physical system. You have a model describing it. As we know, all models are wrong. Some models are useful, and it's describing it to some degree of detail. And it turns out to be capturing roughly some details that we see in physics to a fair approximation of precision. And we've chose to abstract that primitive then in this kind of symbol. And in that sense, that's kind of a microcode. Like, it's like a natural instruction symbol primitive you can then send to the CPU or the implementer, the physics that then run it. But at the same time, it's more fluent than that, right? Because the world isn't just, I mean, it's not a perfect description, and there are leaks and holes, and the instruction set that we have defined in the neuromorphic intermediate representation is not universal. Like, we're not describing all possible ways that you can evolve dynamical systems. So I don't know if that described it. But yeah, I would say it's somewhere in between.
Yeah, it's not microcode in the classical sense, because it captures so much more than what we're used to microcode capturing. But we're treating it as microcode, like it's abstracted
kind of
in the same way microcode would be. Yeah. And some people might criticize this and say, well, it's very contrived to have the base primitive a leaky integrate and fire neuron. But I think it's worth noting that this is extensible, right? If there are, I mean, the reason we've gone with the LIF neuron is because all these libraries use it, right? They use variations of it, like snnTorch does the threshold check to trigger a spike first thing in the sequence of operations, whereas most of the other libraries do it last, causing like some time step delay. In practice with training, it doesn't really matter, but it does lead to subtle variations, and that's kind of what NIR addresses. As long as NIR, the code that exports and imports models, is aware of those subtle variations, then it's mostly all going to match up in the end. But on top of that, other than the fact that we're all using this neuron model, it isn't constrained, right? Like LIF nodes are basically filters. It's circuits 101, EC 101, you learn what a low pass filter is. That's a leaky integrator, right? So it's far more general. Like seeing relaxation processes is very, very common in nature. So I don't want to call it a leaky integrate and fire primitive. It can do that, but it can do so much. But just that one ODE is so much more powerful than just an LIF node, right?
Yeah, I think it's a very important point. Also, that in principle, like, we're not restricting people from composing them, like taking all these things and putting them in series and making very, very complicated, maybe even compartmental neuron morphologies if you want to, right? So the question is, what's the use of that? And again, then we come back to which hardware platform is then relevant for this kind of modeling. But the reason I'm saying this is because I want to go back to the point of co-design, because I think it's important to think about these questions and these instructions from an abstract point of view, right? That thinks, and I agree with Jason here, that I think NIR is one way to progress that abstraction, that way of thinking. But we also have to anchor this in some place, right? We have to run it. We have to win the hardware lottery. Otherwise, we just, yeah, we might as well just all buy shares in NVIDIA and abandon our careers, right?
Yeah, so there's, and yeah, a lot of questions. I'm going to go non-chronologically here. So Mazdak asked, I believe I might have missed where the model is trained. if the training occurs on the original model that we defined, what implications does this have for the weights, particularly when precision levels are of concern? So this is, I don't want to call it a limitation of NIR, but rather it's something that the user needs to be aware of. I'll give you a concrete example, right? Speck's hardware has a certain amount of capacity. If I go ahead and train a model that exceeds that capacity, then I'm not able to load it on, right? That's something that is my responsibility as a deep learning engineer to be aware of before I go ahead and export something to, before I spend a lot of time training something in Norse, snnTorch, LavaDL, etc., if my ultimate intention is to port it onto hardware. So if I know that my end platform is constrained to a maximum of 8-bit weights, then it's my responsibility to, if I want maximum performance, it's my responsibility to know how to train something in a quantized fashion. So that could involve using brevitas and using quantized weights, using libraries that can implement quantization-aware training. So that it's a small price to pay, having extra knowledge required by the user in order to have more extensibility and having more portability, right? Like in a way, if we were to do everything for you, if NIR was to hide a lot of that details from you, then it's much harder to debug, right? Does that address, or did anyone want to add to it? But there are a lot more questions, so we can move forward if there's nothing to add to.
No, I think that's an excellent point. Let's move on, and yeah, feel free to ask additional questions. I think this is a wonderful discussion.
Yeah, Reinhard asks, do you have any plans for non-feed-forward network representation? So we've already got recurrent loops integrated in there, right? So there's recurrent leak integrate and fire neurons, recurrent like second-order Kuba neurons, current-based, which are like second-order low-pass filters. So it's still constrained, but it's not strictly feed-forward, right? I assume you can compose a bunch of recurrents together in order to have more fancy architectures implemented, right?
Yeah, I think I should correct that. Like I said, feed forward, and what I meant by feed forward is not the architecture; it's the evaluation. That was unclear. I'm sorry, but what I meant to say is that we're not updating the network as we're running them yet, so it's not plastic in that sense. But you're very right, Jason, that it's completely arbitrary. So we're literally just defining what's known as directed graphs, and there can be as many cycles in them as you want. You can tie things together in loops, so you can add different parts to it. So in principle, this is doable in the representation. Again, we're back to the question of implementation, right? So what the different chips support, and I think there's excellent support for different kinds of topologies. But be aware of what kind of chip or platform you're targeting. Of course, the simulators are more flexible. I think this also addresses the question by Furkan, who asks how comprehensive NIR is in terms of different neural models and in terms of various network topologies. So topologies, I think, is clear that's arbitrary. You can literally put together whatever you want. The question again is, will it run? Will it blend? Does it blend? Does the NIR model blend? But in terms of different neuron models, as Jason also was saying before, we have I think something around 20 or so odd primitives right now, which represent things like the leaky integrator, a leaky integrator fire neuron, a current-based leaky integrator fire neuron. These kind of relatively general primitives, they're quite versatile if you combine them, compose them in certain ways, but we still don't have more sophisticated neuron models and plasticities, right? So if you want something like the Ichikevich neuron or a very detailed Hodgkin-Huxley model, you can probably approximate it with some of the primitives that we have, but that's to be done. But it's an interesting thing to do as well, because I think a lot of the libraries actually support these things. So if you just add the primitive again and you can just convert it into the existing models in snnTorch, that's already a super valuable contribution. So yeah, great. I hope that answers the question. Unless anyone has anything to add.
No, I think that's good. Maybe one final question. So this has come up in various wording, but so Danish mentions the panel aware about evolvable hardware? I think that just goes towards what the material science and devices community and even the organoid intelligence community are playing with. But then what can we do with other hardware? Is Spinnaker available? Is SynSense available? Maybe I'll let Felix and Bernhard mention how I guess you can get access to this hardware, what plans are, I guess what the roadmap is for getting access to it, etc.
Yeah, as for SynSense, there is no cloud access to our hardware, but development boards can be purchased. So that's usually being done by research groups, but basically anybody who's interested can do that. So feel free to contact us via our website.
Yeah, you can buy it. It's commercial. And Bernhard, Spinnaker?
Yes, so you can easily get remote access to this single chip boards. I'll in a minute I'll copy paste the link in the chat. So this is spinnaker2.gitlab.io, and there are some instructions. I mean, this is under construction, this support, but definitely from academia, it's free to get access. If you want to get your own board, then there's our spin-off, SpinCloud Systems, and they're not yet selling boards, but they are also developing like edge boards, but like more tiny than the ones that I showed. So it's I just suggest to keep watching it and just contact them also if whatever your lab is interested in getting a larger board. Yeah, so I'll copy paste that to the chat.
Perfect. Yeah, and of course LavaDL is also interfaced with Loihi, so I think you can go via Intel Labs. It's always easier if you're affiliated with some academic institution to jump through the NDA hoops that to gain access to Loihi. Otherwise, I want to say that, sorry, Jens, go on.
No, I just want to add another advert because I think Gregor, among others, I think are compiling a list, because there was a question also about where to get more information about these kinds of hardware and neuromorphic computing. And I think the Open Neuromorphic community is compiling a list of all these hardware platforms. But otherwise, like, join the Discord and talk to people. They're the experts. I'm just a computer scientist, but there's a lot of people working on many different and very exciting directions.
Modest as always.
Modest as always. Yeah. Well, I mean, it's a very flourishing field, right? So this particular question was around evolvable hardware, right? Which is also a super interesting thing, but it's dawning on me how complex this is. Like, just recall back to your graph before. There's all the emerging technologies, right? I mean, everything from organoid to memristors to optronics it's a very rapidly growing field, and I'm very excited to see what's coming out. But it's also super complex to follow, I find. So yeah, the link here is the repo for the presentation, so you can see the slides if you want, but they're also all the code. So as Jason said, this is actual running on people's systems. So it's going to be hard to then run the Speck or the Spinnaker thing without the Speck or the Spinnaker systems. But you can train the snnTorch, the Norse model. You can see how, you know, there's nothing magic to it, and the code is there. The NIR repository that's on github.com/neuromorphs/NIR also contains example code from the paper, so you can reproduce that if you want, and you can see what the actual primitives are. Feel free to engage, add issues, ask questions on the Discord. We're very happy to extend this and talk about improvements. Oh, there was one other question from the chat before, talking about visualization. Like, can we visualize these graphs? Because I showed you these lousy ASCII art things with the nodes and edges in the NIR graph. And there's not a visualizer yet, but that would be a cool community project. So I know there are, for instance, visualizers for PyTorch graphs. So it would be wonderful to see these things visualized, so you can see the connections and observe how things are stitched together. So no visualizer yet.
Cool. I think we can wrap it up there. I mean, otherwise the comment section will just turn into shit posting.
But they were excellent questions. I'm really and awesome demos. I think it was a fantastic session. Thanks, everyone.
Yeah, awesome. We'll wrap it up there. Sweet. And Bernhard, get in touch. That's awesome that you're working on a visualizer. That would be, like, I think, more than appreciated. Sweet. All right. Time to go make lunch. Thanks for joining. Don't forget to like, share, subscribe, whatever the young people say nowadays. Join the Discord to stay in the loop of Open Neuromorphics events. I wish I could plug the next event, but I don't remember when it is. So with that being said, we got music. It's wild. All right. See you guys.
Like a boss. See ya.